Hey everybody, Ms. Dietrich here. We're taking a look at how do you model an algebraic equation. So let's start with looking at this word problem. Thomas has $2. He wants to buy a poster that costs $7. Model and solve the equation x plus 2 equals 7 to find the amount x in dollars that Thomas needs to save in order to buy the poster. All right, so we're going to use this green rod to represent x, and we're going to use these little yellow squares to represent whole numbers. So you can see we have 2. And then over here, you can see that we have 7 of the numbers. So x plus 2 equals 7. That's this equation right here. Now, the way that we use these algebra tiles to model the problem, and we're using a simple example to help you wrap your head around this, is that you have to keep an equation balanced. And how might we do that? So if we get rid of these two, recall that the property that says that you can subtract an amount from one side of an equation, as long as you subtract that amount from the other side of the equation remains equal or balanced. That's what we're going to do. So we're taking 2 off of here, and let's take 2 off of here. So if we were to write this out algebraically, so again, the expression was, or the equation rather, was x plus 2 equals 7. And we show 2 being taken off both sides of the equation. That's basically what this is modeling. This would cancel out. We're left with nothing, and that's what we're left with, right? Nothing's left. If we do 7 minus 2, then we get 5. So the answer to the question, how do you solve equations? It's you apply the inverse operations. And why do we do that? This model is supposed to help you understand that. So what's the answer? X equals 5. X equals 5. All right, let's look at some other examples. Let's look at this. Let a rectangle represent the variable. Let a small rectangle represent 1. Solve the equation x plus 3 equals 7. So if we draw a model of this situation, we might draw something like this. This would be x, here's your 3, and then here's your 7. If we remove 3 tiles from this side of the equation, we would have to do the same thing to the other side of the equation. So what does that look like? Looks like this, right? We've crossed out 3 squares on the left side, and we crossed out 3 squares on the right side. So if we just kind of tighten this up and neaten this up, we have x, right? That's what this represents, equaling 4, which isn't that the solution of the equation? All right, let's look at some other simple examples, and then we'll move on to some that are a little more complex. So this is actually showing number 6 here. 1, 2, 3, 4, 5 equals 4, 1, 2, 3, 4, plus x. So same thing, if we get rid of these, right? Get rid of that, and get rid of that. Get rid of this, and get rid of this. Get rid of this, and get rid of this. Get rid of this, and get rid of this. So we're just keeping the balance equal. And if we look at what's left, you can see that we have x equals 1, and that's the solution to the equation. Let's look at a different example. How about, let's look at number 4. All right, so if we're going to model number 4, we need an x, so that's going to be represented green. We need to drag 6 of these yellow tiles. So 1, 2, 3, 4, 5, 6. And then we have to show what that equals. So x plus 6 equals, and it's going to equal 8. So that means we need 8 of these guys. Let's position those. There's 1, 2, 3, 4, 5, 6, 7, and we need one more, 8. All right, so to keep this thing balanced, we have to cross out the same number of these yellow tiles on both sides. So if we got rid of that and got rid of that, it would be balanced. If we got rid of this and got rid of this, it would be balanced. Likewise here and here, here and here, here and here, and here and here. All right, so what have we really done? This was the equation x plus 6 equals 8. We really subtracted 6 from both sides of the equation. So on this side of the equation, we're just left with x, represented here. On this side of the equation, if we count what we have left, we have 2. Now, if we were going to solve this, wouldn't we do 8 minus 6 and get 2? This would cancel out, and we would bring down the x, and x would equal 2. Now, if we were going to do a check, we would take our answer of 2, substitute it in for the place of x, and see if it's true. And if we do 2 plus 6, that does equal 8. That checks. Here's your model, and here's the equation. All right, so now let's look at something that's a little more complex. We're going to use an app for that. Here it is. All right, so here's an equation that says 2x plus 2 equals x plus 5. Now, if we take stuff off of one side of the balance, so what if we take off, how about some of these little discs, which are the whole numbers? Let's take one off. So we took one off of there, and we take another one off of here. What if we got rid of the x's? Let's get rid of this x right here. Let's get rid of one of those. All right, now look at the answer. X equals 3. So that original equation we can solve and get x equals 3 by just taking things off of each side of the balance to keep it balanced. Let's look at a different equation. Let's find one I like here. This one's good. All right, so I'm going to write this down, or let's take a screenshot of it. Let me open this up. Take a screenshot. Go back to this. All right, so there it is on the page. And we're going to explore how would you do this on paper if you didn't have the nice pretty picture to look at. All right, so basically what we want to do is we want to isolate the x on one side. So if we could get it on, we have to decide, are we going to have that be in the left pan or we're going to have that be in the right pan? So if we take off, let's go back to the app. If we take off some of the x's, watch what happens. We took off from this side, and we had to take off from this side to keep it balanced. So now look at the new equation. So let's look at how we would do that on paper. So we basically took this x away, right here. We took that off, and we had to take that off. This is gone, and this is gone. So what are we left with? We're left with, instead of having 2x over here, now we just have x. We still have the plus 1. And over here, what do we have? We still have the 7. So let's go back to the application. See how they're showing you the x plus 1 equals 7? Now, what can we remove to keep things balanced? Can't we take off this? Let's try that. And we took that off, and we got 6. So let's take a look at what that would look like on paper. On paper, we would say subtract 1 to keep it balanced. This would all cancel out. We'd bring down the x, and then we would subtract 7 minus 1 and get 6. So the solution is x equals 6. Now, if we substitute in that value into the original equation, which recall was right here, the 2x plus 1 equals x plus 7. If we substitute in what we got, which was 6, let's do that. Again, 6 is what we got for the x. And let's see if the two sides are equal to confirm our answer. This times this would be 12 plus 1. And we get 13 on that side. And if we add these two things together, we get 13. So the two sides are equal. That confirms that our solution is correct. So we would call this a check. All right, let's explore another example. New equation. Let's see if we can find one. This one's interesting. I like this one. All right, let me take a screenshot of this and put it on a fresh page. All right. Now, when we think about if we're going to isolate the x and put it on one side, usually I like to take the pile that's shorter and get rid of that. So visualize us getting rid of all of that, which means to keep it balanced, we'd have to get rid of all of that. So that's gone, gone, gone. And likewise, if we do the same thing with the stacks here. So let's go back to the app and show what we just did. So we just decided to take off some of the x's. So that's subtracting x's. Let's get that out of the way. We subtract some of the x's. So we have to keep going, and keep going. We got rid of 3 of them so that we were left with just the 1x. So can't we also do something similar with the numeric values? Let's do that. Let's take off, keep going. So we took off 1. Now we're going to take off 2. And now we're going to take off 3. And we get the solution of x equals 2. Now let's go back and look to see how would we model that. So what did we end up doing? This we got rid of. And that means we also have to do the same thing on the other side to keep it balanced. So if you think about what's left, if you look at what's left, I'm going to circle what's left in blue. This is what's left, and this is what's left. So we got x equals 2. Now let's again explore how would you do that on paper? How would you do that on paper? So let's rewrite the equation as it was. It was 4x plus 3 equals 3x plus 5. And one of the things that we were looking at doing first is getting rid of the 3x. So we did that. What would that look like on paper? You would show subtract 3x here, subtract 3x here. And what do you get? Here this cancels out. You're left with no x's, shown here modeled in the pan, no x's. Over here we have the blue, what's represented in blue. We have the 1x, so we can either write it as 1x or we can just put it as plain old x. So what did we do with the numbers? We subtracted 3 from here. Let's use a different color. We subtracted 3 from this side, and we subtracted 3. So let me circle it again in green. We took that off, and we took that off. We took 3 off of both sides of the equation. So this all canceled out, and we were left with nothing. Over here, if we think what's 5 minus 3, we get 2. So 2 is the solution that we just pointed out just a minute ago using the app. Now again, if we go back and take the original equation, which recall was right here, and if we substitute in our value of 2 to see if that's indeed correct, and again, we're substituting in the value of 2, anywhere we see an x. And we're going to see if these two sides of the equation are equal and balanced. This would be 8. 4 times 2 is 8. Over here, this times this would be 6. And if we add this side, we get 11. And if we add this side, we get 11. So 2 is indeed the solution. This would be called a check. Let's do one more example. This one looks good. All right, let me take a screenshot of it. Let's make sure it captured. It did. All right, so let's go back to the application to get our game plan together for how we're going to solve this. So remember, we want to try to isolate the x, or have one pan have the x and one pan not have any x's. So what's the easiest way to do that? It's to subtract x's from both sides. So if I do that, let's take some of those x's off. We took 1 off from each side, so we're left with the 1x. That's perfect. All right, so now we need to get rid of some of these disks, and we have to take off the same number from both sides. So let's take off disks. So I just took off 1. Now I'm taking off 2. Now I'm taking off 3. We're not quite there yet. Take off 4. So I took 4 disks off of each side, and you can see that the answer is 5. All right, so let's go back and see how would you do that on paper. So let's take a screenshot of the equation again. And we'll put this over here. And let's kind of circle what we did. All right, so what did we remove? We removed this, which meant we had to remove that. Now, what does that look like? Take an x off of here, 1x off of here, take an x off of here. 1x is the same as x, by the way. And what are we left with? Well, over here we were left with nothing, right? That's gone. So we were left with the 9. And over here we were left with this x. 1x is the same as x. All right, the other thing that we did is we took these 4 discs off of this side of the balance, which means we had to take 4 discs off of this side of the balance. 1, 2, 3, 4. So that's that. Gone, right? We cross that out. That's gone. So again, how does that look on paper? We subtract 4 from this side, and we have to subtract 4 from this side. So this all cancels out. We're left with nothing. See, that's gone. Over here, what does that equal? Well, that equals 9. Well, let's go back to, actually, let's erase this because that's too many things at once. So here we had the x, here we have nothing, here we have nothing, and here we have the 5. If we just deal with this. This minus this is 5. This, you get nothing. So we have to understand the things that cancel out. All right, so if we go back to modeling using the tape diagram method or those blocks, let's just cover a couple that have negative values. So let me find a few like that. Somewhere in here I have a collection of, this is a good one right here. All right, so let me just move stuff out of the way because I have a lot going on here and it won't make sense with all this stuff here. All right, so if we just focus on everything I have here in this yellow box. All right, so what's represented? Let's put some symbols in. If we were to write this down as an equation, what are we looking at? We're looking at x plus, and then we have 1, 2, 3, 4. And that equals 1, 2, 3, 4, 5, 6, 7, 8, right? Negative 8. 1, 2, 3, 4, 5, 6, 7, 8. So we use red to represent negative. All right, so now the question becomes, there's nothing that's the same. So now we have to do something a little bit different to answer or to model this type of equation. So what we do in this case is we have to get the yellows to cancel out. And how do we do that? To get that to cancel out, we have to actually add red chips to that side. So in other words, what does that look like on paper? That's subtract 4. These red blocks represent subtract 4. Now, whatever you do to one side, remember you have to do to the other side to keep it balanced. So you have to put that over here. Now, you may recall that we talked about the idea of 0 pairs. See, this is a 0 pair, it cancels out. This is a 0 pair, it cancels out. This is a 0 pair, it cancels out. So that all cancels out. Now, if we look at it on paper, this cancels out, right? If you take 4 steps forward and go 4 steps back, you haven't gone anywhere. Now, remember, this is what we added right here, this row. So we think about what's the answer. And let's put it again right here. What's the answer? We have x. So let me write that here. And what are we really dealing with here? If we count up all the red chips, there's 12 chips, and they're all red, so we would say negative 12. So again, if the signs are the same here, remember you're adding the absolute value. This is really the same thing as a negative 8 plus a negative 4, or negative 8 minus 4. It's the same thing. And you get a negative 12 as a solution. So sometimes when you have everything that's originally we had the green, we had the yellow, and then we had the red. And in that approach, you can't take the yellow off because it's not the same thing as taking the yellow off on this side because we didn't have any yellows. So in that case, you have to bring on other color chips to get the thing to balance out. All right, so I think that's a good introduction to this lesson, which was on, let's go back to the title. This is lesson 8.3, Model and Solve Addition Equations.